So for 3.5, we're going to shift our focus we're going to keep factoring, but now we're going to shift our focus to what do we do after we factor. And if you remember back in Unit 2, after we factored, we used the zero product property, and we found the roots of these equations, or we found the intercepts of these functions. So if you remember, roots of an equation, a polynomial equation, a quadratic equation, are the same as the zeros of a function, which are the same as the solutions, which are also the x-intercepts of any of these polynomial functions, right? Where the graph crosses the x-axis. And if we remember, the first way we introduced finding roots or solutions of a quadratic equation was to always check to see if you could factor first. So one way to find the real roots is by factoring. Right? And we always want to see if factoring works first because it's usually a little bit easier and less work. So let's look at this function. We have f of x equals 3x to the fifth plus 18x to the fourth plus 27x cubed. And if you were asked to find the roots or the zeros of this polynomial function, we just start by setting the function equal to 0. And then we always see if we can factor first. And hopefully you remember from the previous lesson, all three of these terms share an x. They're actually also all divisible by 3. So this is definitely factorable. We can take out a 3x cubed as our GCF, and we're left with x squared plus 6x plus 9. Great. We can continue factoring. 3x cubed times x plus 3 times x plus 3, or x plus 3 squared. And then we use the zero product property, and we set both of these terms equal to 0. So we set 3x cubed equal to 0, and we set x plus 3 equal to 0. Or we can say x plus 3 squared equals 0. Okay. If we were to solve for x, you would see that when we divide by 3, we get x cubed equals 0. We would square root. We get x plus 3. There's no plus or minus 0, so just equals 0. But we get x equals 0, and we get x equals negative 3. Well, one thing you should notice here is that this is x cubed equals 0. So you really have 0 as a solution 3 times. And here we have x plus 3 squared equals 0. So you really have negative 3 as a solution, or a root, 2 times. X equals 0 is repeated 3 times because that's to a power of 3. And x equals negative 3 is repeated 2 times as a root. Okay? And the number of times a root is repeated, or a 0 is repeated, that's called your multiplicity of a polynomial equation or function. So the multiplicity is the number of times a root or solution or 0 is repeated. If you have an even multiplicity, then you're going to notice something about your graph. I don't want to give it away yet. And if you have an odd multiplicity, you're going to notice something about your graph. Keep in mind, we've already graphed an even multiplicity, y equals x squared. Y equals x squared is just a quadratic, and at 0, it comes down and turns away from 0 and turns up. We've even graphed an odd multiplicity, y equals x squared, just a linear function going straight through 0. Okay, Let's go look at what this function y equals 3x to the 5th plus 18x to the 4th plus 27x cubed, this polynomial function looks like on Desmos, and see if you guys notice something about what happens at 0 and what happens at -3. Well, hopefully you can see at -3, when the graph comes up to -3, it bounces right back down, just like it was an x squared, and that's because it's an even multiplicity. At 0, it goes through 0 and turns up the other direction. So this is going to be the behavior of every time you have an even or an odd multiplicity. So I'm just going to move this over here to the side. And we're going to label that right here with an even multiplicity. The graph bounces, or it just touches, bounces off the x-axis. Okay, a good way to remember that is just think of x squared. X squared is even. And when you have an x squared function, it bounces off or through the origin, it turns back up the other direction. For an odd multiplicity, the graph crosses through the x-axis. And we're going to focus on multiplicity even more later in this unit when we start graphing more of these functions. We're just going to graph the first couple on this page, and then the last few examples are going to be you just finding the roots, okay? But when we have the roots, we can go ahead and graph this function. We have a root at -3, or an x-intercept. We have a root at 0, and we saw how this function behaved before. It comes up to -3, bounces back down, and then crosses through at 0 because the multiplicity is odd. Multiplicity is odd for 0, it's x cubed, so it goes through. Even because it was x squared, for -3, it bounces down. Okay, let's try one more where we find the roots and then we just use Desmos. We'll sketch the graph together and then we'll go use Desmos and see how we did. Let's try number 2 together, okay? Remember, we're factoring to find the roots. Set the function equal to 0. Anytime you see a polynomial have a degree of 4, 2, and then 0, this is in a quadratic form. So this can factor, or at least we can check to see if it factors. All right, we have x squared minus 9 and x squared minus 4. Factors of 36 that add up to -13. And then these are both a difference of 2 squares, x minus 3, x plus 3, x minus 2, x plus 2. So our 4 roots of this equation, or our 4 zeros of this function, would be 3, -3, 2, and -2, all with a multiplicity of 1, an odd multiplicity. None of these repeat, right? These are all powers of 1, so none of these roots are repeating. Because those are intercepts, let's go plot those. So we have -3, we have -2, we have +2, and +3. Okay, and we're going to cross through on every single one of these intercepts. Let's take a quick look at Desmos and see what this looks like. You can see every single function or every single root the graph is crossing through, and it looks just like 2 sets of parabolas, right? Comes down, goes through, and then if we zoom out a little bit further, you can see this point all the way at the top is 36, and hopefully you realize that that is the y-intercept of this function. So we're not going to go all the way up to 36. We don't have any room. We'll just kind of break our graph here, and it comes back down and curves back up. But this would go all the way up to 36 and then come back down. Okay, and we'll look something like this. Okay, why don't you find the roots of number 3 and then use Desmos and sketch the graph to see what this looks like. You should have had roots of 2, 5, and -5. There was no GCF. It was not in quadratic form. You had to factor by grouping. There's 4 terms. Use that polynomial chart to help you out. So we have -5. we have positive 2 and positive 5. Okay. All with a multiplicity of 1. None of these repeat. So the graphs are going to be, this graph is going to be crossing through each of these intercepts. And it was actually going to look like, we actually know where the y-intercept is as well. It's all the way up at 50, so clearly I'm going to run out of space, but it would come back down and curve back up. And if we go take a look at Desmos, that's what we had here, right? All the way up to 50, it eventually comes back down, but we're crossing through. The most important part is understanding that at this multiplicity, whenever it's an odd multiplicity, it's going to cross right through. Whenever it's even, it's going to bounce. And we'll have more practice with even multiplicity later in this unit. Okay, I'd just like to shift our focus on when we cannot factor a polynomial. Okay, we're not going to graph anymore, just a couple graphing examples. But we've had examples of when a polynomial was not factorable, right? When we couldn't factor a quadratic, we use the quadratic formula. Okay, there's going to be cases where polynomials are not factorable, right? So if it's a quadratic, just use the quadratic formula. For any degree greater than 2, so cubic, quartic, quintic, we're going to use something called the rational root theorem. Okay, and the rational root theorem states, if polynomial p of x has rational roots, meaning real numbers, fractions, or whole numbers, then they must be in the form plus or minus factors of the constant in your polynomial, so the last term without a variable, over factors of the leading coefficient. Okay, and I just want to show you what I mean by that up on one of these previous examples. Okay, we clearly had roots here, real roots. We had roots at 3, 2, -3, -2, +2, and +3. And if you look at the constant of 36 and the leading coefficient of 1, well, there's a lot of factors of 36, but 2 and 3 are definitely factors of 36 over 1. And as you can see, those were real roots here. So what we're going to do to test some of these if they can't factor is we're going to test the possible roots using synthetic division. Okay, and you will know that if one of these roots is true, then you would get a remainder of 0. So let's check number 1 here. We want to find all of the roots. Well, first see if grouping works, right? You're going to see really quickly it doesn't. We can take out an x squared. We're left with x minus 7. We can take out a 2, but there's no way we're going to be left with x minus 7, so grouping does not work. So instead, we need to use the rational root theorem. We want to test all of the factors of the constant, and the constant here is 6, over the leading coefficient, which is 1. Great, so all your factors of 6 are 1, 2, 3, and 6. And all the factors of your constant are just 1, so there's only one factor there. And we're going to test using synthetic. Let's start with the easiest number we could use here, which would be 1. So let's test using synthetic. 1, -7, 14, and -6. Add down, multiply across. 8. Shoot. we get a remainder of 2, which means 1 is not one of the roots here. It's not going to work. So instead, let's try another. And you're going to keep testing until you find one that works. I'm going to speed this up for us, and you're going to keep testing until you tested 3. And you'll notice at 3, this is a factor because when we divide synthetically, we get a remainder of 0. So 3 is a root of this function. And then we can just factor now, this is a quadratic. We know that 3 is a root. This polynomial that's left is x squared minus 4x plus 2. We can just keep solving this equation now to get the rest of our roots. And this is, I would just complete the square here. It's a really easy quadratic function to complete the square. We move the 2 over, add half of 4 squared to both sides. So negative 4 squared is 4. And then factor this down, x minus 2 squared equals 2. Take the square root of both sides, plus or minus root 2. Add 2 to the other side, and you have all of the roots of this function. 3 and 2 plus or minus root 2. Okay. Practice using the rational root theorem. Let's try one more together, and then you'll finish up with 3 and 4, and that'll be it. Okay. Again, number 2, it's not factorable. There's 5 terms. The only way this would be factorable is if there was a GCF, and it's not. There's no GCF there. So we're going to test all of our possible rational roots, which is a lot here. That's okay. 1, 2, 3, and 6, all the factors of the constant, over factors of the leading coefficient. So now instead of 1, we have factors of 1, 2, and 4. So the roots that we're going to test here, this is important, would be 1, 2, 3, and 6. But then we can also test these fractions. We can also test 1 over 2. 2 over 2, which is 1. We can also test 3 over 2. We can also test 6 over 4, which is 3 over 2. We're not going to test that twice, but these are all factors, so let's write this up here. 1/2. 3 over 2. We can also test factors of 1 over 4. 3 over 4. But as you can see, there's a lot of possible roots that we're going to test here. I'm going to speed this up for us. The first one that was going to work was going to be 2. Okay? Don't worry, there's not a lot of homework problems. I know these each take a while. Okay? But you're usually going to want to start testing with +1 and -1. Those are the 2 easiest and quickest ones to test, and then just work your way up. Add down, multiply across. Oops. -13, -26, get -8, -16, 3, 6. There's a remainder of 0. We are left with 4x cubed minus 13x squared minus 8x plus 3. Set it equal to 0. We have one root that works. We need to keep going. There's some more real roots here. Again, you can test to see if grouping works here. It doesn't. So then you're just going to keep using the rational root theorem and testing these values. The next rational root that was going to work was going to be -3/4, and we can now use these constants. We don't need to go back to our original. So 4, -13, -8, and 3. Add down, multiply across. -3, -16. 4 goes into 16 4 times, so we get -12. Or sorry, negative times a negative gets us +12. 4, and there's our -3 for our remainder of 0. So now we're left with 4x squared minus 16x plus 4 equals 0. And this is a quadratic. And now we can just solve the rest of this equation by factoring, right? We have a GCF. We can take out the 4. We're left with x squared minus 4x plus 1 equals 0. Again, this is a really easy function to complete the square. If you want to just use the quadratic, you can do that. We're going to add 4 to both sides. So we factor down to x minus 2 squared equals 5, and we're going to take the square root. I'm going to move this up here. We have x minus 2 equals plus or minus root 5. So we have x equals 2 plus or minus root 5 here. Sorry, we need to be careful. This is actually a -1. We're subtracting that 1 over, my fault. So this would give us a 3. 4 minus 1 is 3. We're not adding 1, so we get 2 plus or minus root 3. Okay? And you're factored all the way down. You are done when you get to the quadratic, and you find the rest of the roots by solving the quadratic, either by completing the square or using the quadratic formula. Okay, I know these are a lot of work and they take time. Why don't you pause the video and just work out numbers 3 and 4, or the video will pause on its own, and then I'll put the solutions up when you're done. I'll help you get started. For number 3, maybe try testing -1/2, okay? But your possible roots are plus or minus 1, 2, and 4, factors of your constant, over factors of 2. And then for number 4, factors of, well, why don't you solve that one first, because you can definitely take out a GCF of 2 there. Those are all even numbers, and see what you get. Okay, for number 3, the roots that we had for this equation were -1/2 and 1 plus or minus root 5. Okay? Either a quadratic formula or completing a square to get these last 2 roots. For number 4, you were going to get -3 with a multiplicity of 2, so it was going to repeat twice, and then -1 as a root, 0, and +1. Okay. I know these problems take some time. The most important piece of this lesson is that you're able to test these roots using synthetic division, and the possible roots that would work are plus or minus the factors of the constant, the last term in the polynomial, over factors of the leading coefficient, the coefficient of the first term. Okay? Plenty of practice tonight. I'll answer any questions you have in class.